This is going to be a continuation of what we talked about yesterday, and I guess the focus of today's lecture is going to be more on transfer learning. Okay, so what's the motivation here? What ideally we'd want to do is we want to learn representations, meaningful representations, so that we can start learning new tasks or start learning new concepts fairly quickly, right? And in fact, in most of the machine learning applications that we're seeing today, you typically measure performance of classification or regression using hundreds of thousands of training examples, whereas for human learners, it's obviously the case that you might only need few training examples. So how can you transfer knowledge abstracted from previous concepts or from previous classes so that you can start learning new concepts from few examples, right? That's sort of a general idea of any intelligent system should be able to do that. And last time I've shown, yesterday I showed you this little demo. I wanted to show you again that, you know, it's certainly the case that if I show you one particular concept, you can grab it, right? Same thing for other concepts. So it really is an interesting problem, and it's a very fundamental problem of how can you learn new concepts or new classes from few examples, which is a fairly high-dimensional statistical object, right? So how can that be done? And just to reemphasize, in traditional supervised learning, we're typically dealing with the problems where I've shown you a bunch of images of one class, a bunch of images of another class, and then I'm trying to test or recognize what we see here. Whereas the idea of trying to do transfer learning or learning how to do transfer learning is the setup that we're going to be having today is you might have millions of unlabeled images, or lots of unlabeled images, and some partially labeled images. And then the question is, how can you start getting to know new concept or new class fairly quickly, maybe just from a single example, okay? And then start testing of what that is. Oh, right, and then this is a key problem in computer vision, speech perception, speech recognition, NLP, and lots of other domains. Okay, so this is going to be the talk outline. I'm going to be focusing on one particular model. It's called Hierarchical-Deep Model, and this is the idea of combining two different models, undirected graphical model with directed graphical model. So deep Boltzmann machines with something that's called hierarchical Latent Dirichlet allocation model, and I'm going to show you some applications and finish up with conclusions. Okay, so hierarchical Bayesian models, we've seen that briefly yesterday. The idea of building hierarchical Bayesian models, they're fairly straightforward. The idea is that you define some likelihood function, probability of observed data given some parameters, W. You typically have some prior distribution over the parameters, and you're interested in computing the posterior distribution of parameters. Now, in most of the interesting applications, instead of just having a flat prior, you might be interested in defining a hierarchical prior, right? So this is one particular example of a directed graphical model where you might say, you know, maybe cows, horses, and sheep should share certain parameters, such as the mean and variances, for example, and vehicles should share other parameters. So you'd expecting to see cows, horses, and sheep to be distinct from trucks and cars and such. And this was done a lot, particularly in computer vision community. I just wanted to point out there's been a lot of work trying to get to this idea of trying to do learning from few examples using hierarchical Bayesian approaches. Okay, so the hierarchical deep model, the idea here is that we're going to compose the hierarchical Bayesian models with deep networks. And these are fairly two influential approaches for unsupervised learning, right? Deep networks. We've talked a lot about deep networks, and the way to think about deep networks is really thinking about them as part-based hierarchies, right? You learn multiple layers of nonlinearities. You can do it in unsupervised fashion. You can use labeled data to slightly fine-tune your model. But it really comes down to the fact that, you know, you're defining these part-based hierarchies where you can say, well, hand is a part of the forearm is a part of the arm, and then you get a human object, for example, right? So you're putting little Lego pieces together to get some representation. But there is another notion of hierarchies, which is a category-based hierarchy, right? So here you're explicitly representing category hierarchies that would allow you to share abstract knowledge. And you can explicitly identify only a small number of parameters that are relevant for a particular novel concept that you're learning, right? So here, for example, you can say that canary and eagle are part of the bird and they share certain parameters and so forth. And you can see that these two notions of hierarchies are quite different, distinct from another, from one from another. Okay, so and we need both to do the kind of learning that we're going to be doing today. So what's the motivation here? The motivation is fairly simple at the high level. Imagine that you're seeing that particular object, and it's the first time you're seeing that object. Well, you can say there is a notion of supercategories. You can say that, well, a Segway might look like a funny kind of a vehicle, and you might know a lot about vehicles. There is a notion of high-level parts that are shared with other classes like wheel, handle, and post. And there is also a notion of low-level features, right? Low-level features like edges and combination of edges that get composed into parts, and then parts get composed into object. And there is a certain relationship between these objects and the Segway, right? And what we're going to do now is we're going to do two distinct approaches. We're going to use deep learning. In particular, we're going to be using deep Boltzmann machines and trying to modeling this piece here, low-level features, and we're going to be using hierarchical Bayesian models and trying to model the explicit hierarchies or put some more structured priors to relationship between different objects. Okay, so this is the model, and I'm going to get into specific details about that model. We're going to be using deep Boltzmann machines, something that we talked about yesterday, to learn a low-level generic features, and that can be done in unsupervised fashion. You can use millions of images and just to figure out what images look like. There is a notion of high-level class-sensitive features, and these class-sensitive features can be capturing certain perceptual structure of a specific concept, right? So and there is also a notion of hierarchical organization of categories. So you may say that these different categories, they express priors on different features that are typical of different kinds of concepts. So for example, here you might say that animals should share certain high-level features. Vehicles should share certain other high-level features. Okay? And so let's just revisit the deep Boltzmann machines just as a reminder, and then we can see how we can actually put these two models together. So deep Boltzmann machines, just as a reminder, you're building it from unlabeled inputs. You're learning this hierarchical representation, and hopefully the high-level features will start capturing high-level structure that you're seeing in the images. And from yesterday's talk, just as a reminder, the probability of observed input here can be written this way, right? So you have interaction terms, W1, W2, W3, that are modeling interactions between V and H1, H1 and H2, H2 and H3. Right? So this is a standard Markov random field with hidden variables. And all connections are undirected. And there is a notion of bottom-up and top-down. Now, we can look at the joint probability distribution over all of these random variables, and we can decompose them into two terms. Okay? The first term we can call conditional deep Boltzmann machine, and the last term we can call the prior term. Okay, that's a standard decomposition. Now, within the deep Boltzmann machine framework, this term you can get by just marginalizing out over these random variables, and it's typically a fairly complicated prior term. And you can really view conditional deep Boltzmann machine in this way, where we're conditioning on the states of these random variables, condition on the states of these random variables, we have a conditional deep Boltzmann machine. Notice that the normalizing constant here, or the partition function, will depend on the states of these random variables. Okay, so this is unlike deep belief network. Here you have directed connections from the top, and then you have an undirected connections at the bottom. Okay, and the whole idea is in spirit similar to the idea of pre-training or greedy-wise learning of deep belief networks. The idea here is that you can take this prior term and replace it with more structured hierarchical prior. Okay. So how can we do that? Remember, with deep Boltzmann machines, we typically approximate this posterior over these hidden variables with a fully factorized tractable distribution. So we're typically using mean field approximation, and we can optimize on that, and we can write down the variation low bound, right? Something that we went over yesterday in yesterday's talk, where we have a likelihood term, you have an entropy functional, and this term here just comes out of the likelihood term here, and the idea is exactly the same as the idea behind pre-training deep belief networks, where you're replacing the last term or this prior with something different. So typically with pre-training of deep belief networks as well as deep Boltzmann machines, you're replacing this prior with another undirected graphical model, and that's how you end up stacking these models together. Here we're just going to be replacing it with something more structured. Okay? So it's a little bit, there's a little bit of math involved here, but the end message that I want to communicate is as following. You can learn a deep Boltzmann machine. You can use variational inference to infer the top-level latent variables, the states of the top-level latent variables, and you can just fit. In this case, we're looking at a latent Dirichlet allocation prior, okay? Or you can fit any type of hierarchical prior. Okay. So let me quickly give an overview of hierarchical LDA model and see how we can use it here. Okay, so there is one thing that's interesting about particular model, that particular model LDA, is that it's using bag of words representation, right? This is you have an object and you can represent it as bag of words. So you define words, maybe little patches of images, or in a document those would just be represented as words, and you just put them in the bag. And a lot of computer vision people, it's a little bit funny because LDA models, they work fairly well in a lot of computer vision applications, and it's a bit ridiculous because you're losing all the spatial structure in the images. The intuition here is that behind LDA model is that the documents might contain multiple topics, and so here is a document and you're just representing it as bag of words. Here's another document, and again you're representing as bag of words. You're just counting how many words occur in that particular document. Okay, so it's a very naive representation to some extent. And this is the output of the LDA model. So what it does is you have a text document listed here, and these are discovered topics. Okay, and the idea is that, you know, it's just an illustration here that in this document you have topics related to art. So each topic here represents a distribution of words. So under arts, the word film and show and movie, they have higher probabilities. Under the topic children, the word children and women and people and child have higher probabilities and such. So it basically discovers that this document contains these different topics. Now, what's the probabilistic model behind this model? It's a fairly simple model. It's not hard to fit that model, but the idea is the following. For each topic, you predefine how many topics you want to have. For each topic, you draw the distribution of the words for that topic from a Dirichlet distribution. Now, for each document D, you draw topic proportions. Topic proportions essentially say which topics are more common and which topics are less common in that particular document, right? And then for each word in the topic, you draw topic indicator variables that basically say which topic that particular word is coming from. And then you just draw that particular word from a multinomial distribution defined by the topic, right? So here's the intuition. Let's just see how you can generate the word opera in that particular document. The way you would generate the word opera in that particular document is that you would draw topic indicator variables that would belong, so that Z would belong to art, right? And then you draw a word from that distribution. So opera appears, I guess, somewhere here. And there's a certain probability associated with it. Okay? Now, in that particular document, you can also see that art and budgets and children topics, they are more common, and education is less common. So when you're drawing document-specific topic proportions, you might say, well, these topics are more common and this topic is not as common. Okay? So that's a generative model defined by the LDA model. It's a fairly simple generative model. Now, in our model, what we're going to do is we're going to assume that the states of the latent variables at the third level in a deep Boltzmann machine, we're going to treat them as words and in a document, right? And each image or each input is going to be represented as a document. So we're going to be putting an LDA prior on top of the activities of the top-level variables. So in this case, we can think of words as activations of the DBM's top-level units, and we can think of topics as distributions defined over the high-level units or high-level parts, right? So the intuition here you should have is the following. These are DBM's generic features. These are low-level features that the Boltzmann machine finds. These are high-level features or topics that it discovers, and these are the images and documents. In this case, each topic here is represented, is made up of words, or these features, and each image is made up of these topics. Okay, so it's a compositional, it's a hierarchical decomposition of that model. So again, just to re-emphasize that, the activities of the top-level units, they represent words in a document. Each image is, you can think of it as a document, and you have that decomposition. So notice that it nicely finds, if you look at these high-level features or topics, each one of those features defines a distribution over these low-level features, okay? And it sort of finds interesting type of high-level structure in images. It's also an interesting thing that for objects like apples, for example, or other objects, it sort of decomposes this image into shape and color. That's something that the model discovers, a good way of representing images. And the interesting thing about this model is that there is no image-specific priors that we're placing into these models. These are just discovered by the model, right? Now, one question is that, can you extend this model to modeling hierarchies? Because that's what we're after. And the idea here is it's a very simple extension, but the idea is the following. You draw global topic proportions, and these come from some prior. Then there is notion of superclass-specific topic proportions. So here you might say that animals topic or the animals supercategory might have certain high-level features, whereas vehicle supercategory might have certain other high-level features. Right? You want to make a distinction between the two. Then you can draw class-specific topic proportions. Right? So for example, horses might have certain high-level features, and cows might have certain other high-level features, but there is a sharing happening at this level here. And then you're drawing document-specific topic proportions or image-specific topic proportions, right? And there is also a non-parametric extension of this model. It's called hierarchical Dirichlet process. It's also fairly straightforward to let the number of topics k here go to infinity. Pictorially, what the model does is the following. Here's just a visualization of high-level features of the topics that the model discovers, and then you can say, well, there is a superclass-specific topic proportions. So, for example, fruits, apples, oranges, and pears, they have these high-level features, whereas aquatic animals have these high-level features. So notice that there is nice separation of high-level features. Then there is a class-specific topic proportions. You might say apples, typically they have these high-level features, and oranges have these high-level features. Notice that oranges, you have more orange color associated with oranges. And then now you have image-specific topic proportions. So you might say this apple, and this is the reconstruction of this apple, has these high-level features. So it's yellowish and round, versus red apple, you have again shared high-level features, and then red color component associated with those apples. Okay, so there is a notion of hierarchy. So you have a big, lots of high-level topics. Typically in our models we have about 1,000 of these high-level features, and then there is a nice separation of categories into different supercategories that carry information about class-specific or superclass-specific high-level features or parts. Okay. So, and so far we've been making assumption that we have a fixed hierarchy, right? So now the question is, can we actually learn what that hierarchical representation is, right? And this can be accomplished using what's called Chinese restaurant process prior, which is essentially just a prior. It's a prior of a partition of integers. So you can think of it as this Chinese restaurant process defining a distributional partition of integers. It's a fairly simple prior to use, and it works fairly well in a lot of cases. The idea is the following. You can think about the CRP process as the following. You have customers entering a restaurant with unbounded number of tables, and an nth customer that walks into the restaurant occupies table K according to these probabilities, right? So typically you would sit at the table that's most popular, where nk is the number of previous customers at table k, and there is certain probability alpha that you would occupy a new table. Okay, so this is and customers here are integers, and tables would be clusters. So it's fairly simple process, and you know, to think about this process is you know, clusters that are more popular will get more data, and then occasionally you'll have new clusters being formed or new partitions being formed. Right? Pictorially, in terms of putting this type of prior on the hierarchical representation, this is what happens. Suppose that we have a new class coming in, okay? Well, with probability, because we have 3 classes, with probability 2 over 3 plus alpha, that class would be assigned to this superclass, okay? So this would be the hierarchical representation. With probability 1 over 3 plus alpha, you would be assigned to this superclass. And then with probability alpha over 3 plus alpha, you would create a novel superclass. Okay? So this is just a very simple prior that you can put on your hierarchies in order to figure out, to have probabilities associated with each hierarchy. And the expected number of classes grows as alpha log n. And there is a certain extension of this process called nested Chinese restaurant process that essentially extends CRP to the nested sequence of partitions. Right, so you can define, now at this case, you can define exactly the same process, so you can essentially define a prior probability over different tree hierarchies, right? So each particular instantiation of the tree would have a probability associated with it, would have a prior probability associated with it according to this process, okay? And of course, the depth of the tree would be controlled by this hyperparameter alpha, okay? So now, having all of these in K in our hands, we can define the following model. We can draw Z, which is a random variable from the nested Chinese restaurant process prior, which is just essentially a non-parametric prior with tree structures. So each tree structure will have a probability associated with it. Once you draw a particular tree hierarchy, then you're going to draw the states of the high-level units, H3, these guys, from a hierarchical Dirichlet process, which is just an extension of hierarchical LDA. And then conditioned on these states that you've drawn from an HDP prior, you're going to be drawing observed variables from a conditional deep Boltzmann machine model. Right? Now, the intuition that you should have here is that deep Boltzmann machine models and deep networks, they're very good in terms of figuring out exactly the locations of different pixels or the location of different parts or different pieces that should be glued together in order to get a reasonable image. Whereas these hierarchical models are good in terms of figuring out the overall hierarchy. What's the relationship between different parts in the hierarchy? How different objects relate to each other, right? And it's important for applications such as transfer learning, or learning from few examples, novel concepts from few examples. And this is unlike a lot of standard statistical models. Here, in addition to inferring parameters of this model, you're also trying to infer the hierarchy of how these parameters are being shared together. This task becomes much easier if you knew what the hierarchy is, but often in a lot of situations you don't know what the hierarchical representation is, and you're trying to learn what that hierarchy is. That becomes a fairly hard task. Right, so this is what we've done with one particular application. This is a CIFAR dataset. Again, you can learn low-level generic features using deep Boltzmann machines, something that we talked about yesterday. And you can try to learn high-level features as well as the hierarchy from labeled examples. And you can use MCMC methods, and that's something that you will hear about in the future talks about Markov chain Monte Carlo method. So there is an inference stage here that can be done. It's not too bad. It's slow, but not too slow. And this is the type of hierarchy. It's just a visualization of the hierarchy that the model is learning. You know, you have aquatic animals, fruits, humans. This is just part of the hierarchy, and this is learned. And you have high-level features such as an apple is being represented by these high-level features. And you also have low-level representation, low-level features, low-level generic features that you learn from millions of unlabeled images, right? So most of the representation here is actually learned from the data. And this is the type of hierarchy that the model is able to discover. A lot of it looks reasonable, like you have reptiles, you have aquatic animals, you have different trees and such. You have vehicles and you have humans. So there is some reasonable hierarchical representation that the model is able to learn. So it's not too bad. But now the question now comes, we've learned all of these representations, low-level representations, high-level features, the hierarchy. So how can we actually do transfer learning? What's the key idea here? Well, let's look at a particular example of how that can be done. Suppose I show you an apple. That's the reconstruction of the apple. And here I'm displaying the top, 10 most active high-level features. There's another red apple, and again, this is what it discovers. Notice that there is a sharing of shape and decomposition of shape and color. Now, if I show you oranges reside under the same part of the hierarchy, so they're going to be sharing a lot of high-level features. So there's a notion of sharing happening here. Now, suppose I show you a single example of a sunflower, right? Turns out that these are the high-level features that the model assigns to the sunflower, and it resides under the same hierarchy. So it essentially says sunflowers are like apples and oranges, like it's orange and it's round, right? That's what the model discovers, with the exception of these two features. So it discovers there should be a dot here, right? But notice that all of these high-level features are being learned based on the background knowledge, right? So all of these representations are already learned, and so the model just has to figure out that this is what makes a sunflower a sunflower. And if you look at other objects like dolphins, notice that they have quite different, they reside in a different part of the hierarchy, and they have quite different representation. So the idea here is that you're trying to learn the hierarchy for sharing the parameters, and that particular sharing allows you to share the parameters. It's quite important for being able to learn new concepts from a few examples, because all you have to do, based on a single example, you just have to figure out what particular features make up that examples, what are the important features. And there's a lot of sharing happening between other classes. Okay? And this is just a slide to show you that if you're using other models, our model can do much better. But of course, it will do much better. Otherwise, I wouldn't be showing you that model. But a much more interesting thing to look at is if we apply this model to handwritten characters, this is what a deep Boltzmann machine learns. These are standard strokes and such that you've probably seen before, but these are the high-level features that it learns. Notice a lot of them do look like strokes. And these are the clusters or supercategories that the model learns. So you can think of, for example, each of these characters defines distribution over these high-level features. Each of those high-level features defines a distribution over these low-level features. So there's a natural decomposition here. And it does a pretty reasonable job in terms of figuring out how different objects should be grouped together, different characters should be grouped together. And you can do much better compared to, for example, models like deep Boltzmann machines or latent Dirichlet allocation and such. You can also simulate new things. This is a fun part with generative models. You can try to simulate new characters. So for example, if I've shown you this is the real data meaning that these are humans who draw these characters. And now I may ask the model to generate me characters of this form, new characters of this form. And this is what the model does. This is a simulation of a new character, and this is a simulation of another new character, and so forth. So if you look at these characters, the structure of these characters sort of similar to the real data that you see. But the interesting thing here is that if you look at the training data, there is nothing like that in the training data. So these are completely hallucinated characters that the model does generate. This is another thing, these are another alphabets. Notice that again, the structure here sort of resembles the structure of what you see at the high level. And it's because you're putting this particular hierarchical prior or very structured hierarchical prior, which defines which types of characters you want to generate, right? And it does a fairly decent job. You can also try to see, well, how well does the model does in terms of learning from few examples. So here I'm showing you three examples, and these are generated examples. Just based on 3 examples, this is what the model generates. And this is the superclass, where it borrows information from that particular superclass in terms of which parts you're expecting to see here. And it does, like for example here, that's a hard one, right? That's a hard one to generate. It does find that this is the most relevant class, and it generates something fuzzy. But in a lot of cases, it does a pretty good job in terms of capturing the underlying concept just based on 3 examples. And it's able to generate a variety of sort of similar characters. So it's not too bad in terms of figuring out what the character looks like just based on 3 examples. You can also do fun things like applying this model to motion capture data. So suppose I show you that particular walk, that's a walk, and I show you a drunken walk. Now, if you look at these motion capture data, I guess Graham was talking about motion capture data. These are 56 markers sitting on the human body, and if you look at the relationship between the walk style and the dynamics, it's quite nonlinear. But suppose I also show you a sexy walk here. So this is a sexy walk. And now just based on that particular play, you should be able to figure out what sexy walks are, right? And indeed, if you try to build the model and you build some form of hierarchical prior that basically says how different walks are related to each other, so you can transfer knowledge between related walks, you can do much better in terms of differentiating particular styles of walk from other styles of walk based just on a short time series data. Okay, and the interesting thing is that the same model can be applied to text, speech, video, or any high-dimensional data. We're not making any assumptions about that we're working with images or video or motion capture data. It's the same model. So let me just briefly talk about a few other hierarchical models. One question that typically pops up in a lot of applications is that if you want to do object recognition or object categorization, it's just one example. You typically would say, well, I would need at least to know the mean of the object or the prototype, and I would need to know the variances or some form of similarity metric, saying how different objects relate to each other, right? So here's an example. If I show you these cars, sorry, you may say that, well, the color features, they vary fairly strongly, but the shape features don't vary at all, right? And that's what quantifies the notion of a car, right? Now, suppose I show you a van and I show you a new class, that's a new concept, right? And you might say, well, if I show you just a single example, it might tell me something about the prototype, how a van should look like, but it doesn't tell me anything about variances, right? It doesn't tell me whether all vans should be white or there is, and shapes could be different, or the shape should be the same and colors could be different, right? Just a single example doesn't tell you that. So here's one way of doing that is you may say, well, here's a particular example. You might say, well, suppose in some high-dimensional feature space, this is the representation that we learn. These are dogs, sheep, and horses. They vary a lot across X dimension, but they don't vary much across Y dimension, and same thing for cars. Now, if I show you a new category cow, right, then you might be able to, based on the single example, you might be able to estimate that this is roughly what the similarity metric for that cow is, right, if you find the right sets of features. And maybe you can basically figure out, well, animals really, they vary among this dimension, but not across this dimension. But for vehicle, it's the other way around. Okay, so so basically, again, that comes to the same question where how do you group related categories together, right? So that you can borrow information from classes within the same category. Right? And this is the model that I've shown you briefly at the very beginning. The idea here is that it's a very simple probabilistic model. You can define a model where you say that each observation has a Gaussian distribution with mean and precision terms, but there is a certain structure, there is a certain hierarchy to that model. And you can also define the hierarchical model. You can define conjugate normal gamma price over the means and precisions and so forth. And you can put this hierarchical prior on how different objects relate to each other. And as before, the interesting thing here is that you can try to infer what that hierarchical organization is based on the data. And here's again, this is just the way that this was MSR dataset. It discovers, meaningful categories. You can do fun things like object retrieval. So if I show you a query image, this is what the model does when you're using hierarchical Bayesian model, and this is what it does if you just ignore learning the similarity metric altogether and you just say based on nearest neighbors in the feature space, this is what it does. So it completely confuses sheep with chimneys and such. Of course, this model fails as well because this is actually a failure. This is sheep, is not a cow, right? So this is where it fails. You can also try to do something a little bit more ambitious. Is you can ask the model to say, well, when have you encountered a novel category, right? So here is one particular test. You show the model many unlabeled examples, and you don't tell the model how many classes you have. You just seeing new examples, and then the model is able to break up, these examples into the existing categories. So it's seen these categories before, and it's able to create these new categories or new classes, right? And in particular, for example, images of skies are very distinct from all images in a database, so that the model essentially is going to say, well, that's going to be my new super category. It's going to be my new category called skies. So again, it's a fairly important problem, at least in the computer vision community. You can also try to take it a little bit further, these hierarchical models, and try to consider more challenging task, object detection task. And just to do a little bit of amusement, if you look at that particular image and your object detection detects this, so can you guess what the object is trying to detect? Like, what would be your first guess? Bad, right? Yeah, I mean, obviously it's detecting bad. Well, actually it's detecting bread. So that just basically is telling you that the object detection systems that we have today are not very sophisticated. It's a very hard problem, but state-of-the-art object detection would tell you that this is bread. Right. So now one of the questions we're facing today is that if you look at the distribution of objects that you see in your real day life, it has this power law distribution. This is a particular sun data set. You have certain objects like doors and windows and cars, and you have lots and lots of these objects. And you have certain other objects that you have few examples for those objects, like elephants and such, right? How many times in your lifetime you see elephants? Maybe 1 or 2 times, but you can quickly recognize elephants. And this is sort of the idea that, you might have lots of cars and vans, but you might have only a few trucks and buses, right? The question is, can you take information from these classes and learn something about these classes, right? And it's interesting to note that the rare objects typically fairly similar to frequent objects, so they share a certain structure with frequent objects. Same thing goes for chairs. You might have lots of chairs, but you might only have few deck chairs. And you want to build a system that can recognize deck chairs. And somehow you want to be able to borrow the examples from armchairs and chairs and swivel chairs, right? Now, in many of the state-of-the-art object detection systems, they use fairly sophisticated models, and it's a lot of research happening in terms of figuring out what these features are. A lot of research in the deep learning community is also focusing on what these features are. But in the end, if you look at state-of-the-art object detection systems or object recognition systems, they all have very simple form. It's a linear regression model or logistic regression or something fairly simple, right? And you typically do object detection by testing just sub-windows and figuring out what you're seeing in each sub-window. But here what we can do is we can define hierarchical prior with the parameters of a particular discriminative model, and we can try to learn the hierarchy. Right? And here's one particular example. Again, if you have 185 examples of car, 27 examples of van, and then 12 examples of truck. But if you're able to figure out that they're all basically the same, so you can borrow a lot of information from cars, and that information is going to be flowing to what trucks should look like, you can do a lot. So this is a representation of a car, kind of looks like a car, and this is a representation of a truck. And indeed, if you look at the hierarchical models, then you can do detection much better with just seeing 12 examples of a truck compared to a model that just ignores the hierarchy altogether, right? And in that particular case, the underlying model used specific image-specific features like hogs, but as we go forward, the ideal thing would be to use deep Boltzmann machines or deep models to figure out what the underlying features are. Okay, so these are just more examples of a detection. Sometimes it does okay, but in a lot of cases it fails to detect trucks. This is another example of detecting domes. Again, existing systems, they fail here, and if you're using hierarchical models, it typically works better. Sometimes it fails as well. A fun thing to look at is to look at the types of clusters or the types of hierarchy that it discovers. Sometimes it puts cars and hats together because cars look like hats, and sometimes it puts bottles and humans together. Like this is a person, this is a bottle, and this is a well-known fact. If you have a bottle detector, you can detect people because people look like bottles, right? And that's something that comes out of the model. You can also try to do a little bit more advanced models, and that really has to do with trying to define a generative models of matrix factorization. So here's the question of, if you have image bases, or if you have relational data, you have gene expression data, how can you try to figure out mathematically what kind of structure you're seeing in that data? And this is the work by Roger Gross at MIT. The idea here is that you can try to define, go above just defining simple tree-based hierarchies, but you can go beyond that and try to define context-free grammars. And based on that, you can try to use more sophisticated techniques and try to figure out what kind of structure you see at the data. And Roger is here, so if you want to more about this work, you should talk to him. So finally, in the last 5 minutes, we've talked about Boltzmann machines, we've talked about hierarchical models, and the idea really that I wanted to communicate here is that you can combine more structured hierarchical models with deep networks and try to look at these compositional models. Of course, one of the big problems defining these more complex models is how do you do inference in these models? And that's a challenge, and a lot of research is being dedicated towards solving that. In particular, when you're dealing with high-dimensional data, or you typically end up having a probability distribution that's highly multimodal, or the energy landscape is highly multimodal. And the really question comes, how can you explore a space where you have lots of isolated modes? And it really, a lot of models that we have right now are really suffering from the fact that it's very hard to explore a distribution with many isolated modes. So if you, for example, if you're trying to sample from the model, a standard GIP sampling would just get stuck, and that's very bad, okay? There are lots of advanced techniques. So I just wanted to introduce briefly a couple of techniques. It requires a lot of, it requires a little bit of machinery behind MCMC methods, Markov chain Monte Carlo methods, but I just wanted to give you maybe just a 5-minute tour de France about what's out there. Okay, so you don't have to look at specific details, but I'll give you some intuitions. Once you hear the lectures on Markov chain Monte Carlo, it will be more clear. But the idea is that, again, when we're looking at the posterior distribution, such as when we look at hierarchical LDA model, we have to deal with that problem. Or when we look at deep Boltzmann machines, we have to deal with a normalizing constant. We have to be able, when we do learning, we have to be able to take derivatives of the log of the normalizing constants. One beautiful method for trying to deal with that problem was the method called tempered transitions. It was proposed by Redford Neal in '94, and it's a fairly simple algorithm. If you actually code it up, it's about 5 lines of MATLAB code, and it works fairly well. The idea is the following. Suppose you have your original complicated distribution. That's a very nasty distribution. And you have some distribution that's more spread out or much easier to sample from. So for example, that could be a Gaussian distribution, could be a fully factorized distribution. One way of defining, and you have a sequence of transition, or you have a sequence of distributions linking the simple distributions to this more complex distribution. One way of defining those distributions is just take your original distribution that's fairly complex and just raise it to some power, beta. And beta should be less than 1. These are sometimes called inverse temperatures. So the intuition here is that when beta is 1, you have your fairly complex distribution. As beta becomes 0, in which case you might be able to get almost uniform distribution. That would be a uniform distribution. right? And you define for each one of those intermediate distributions, you define a transition operator that leaves P sub S invariant. That basically means that you have to figure out a Gibbs sampler procedure, for example, a Metropolis-Hastings procedure when you're trying to sample from that distribution. And the idea of the algorithm, it's fairly simple. What it does is it tries to take a sample and systematically move from the complicated distribution to either the sample distribution to your simple distribution and then back. So it's like you have a sample particle that moves around. It goes to the distribution that's easy to sample from, so it moves around in the space and then it comes back. So it does this systematic move, and then there is a certain accept probability. You're accepting the probability with a standard Metropolis-Hastings operator. Okay, so this is if you use, for example, if this is your training data, and this is a NORB data set, and you use plain Gibbs sampler using stochastic approximation using Gibbs sampler, this is what it does. And remember last time when I was showing you a similar picture, I've mentioned that it typically gets stuck. So this is the case where it generates too many people with guns, right? Like these guys. Whereas if you're using learning with temporal transitions, you can explore the space much more efficiently, so it does reasonably better in terms of exploring the space. It's a fairly simple technique. I would advise you to try it out. There are also other techniques. Just a couple of minutes, for a couple of minutes, I just wanted to point out another technique called simulated tempering. And the idea behind simulated tempering is you're trying to sample from this joint distribution, where again K is your inverse temperatures, but you have this notion that you have to define these predefined constants. You have to define these W sub Ks. And the main problem of simulated tempering is that somehow these W sub Ks, they need to be proportional to the normalizing constants. So simulated tempering, it's a very powerful technique. It also is similar to temporal transitions. It tries to move between temperature levels. So it tries to go to the easily sampled distribution, move around in the space, and then go back. The problem is that somehow to use that technique, you roughly have to know the normalizing constants. But obviously you can't do it, so typically you would do pilot simulations, try to figure out what they are, so it becomes a fairly complicated process. There is one particular thing that I just wanted to draw your attention to. I'm not going to get into the theory behind these methods, but there is one interesting subfield in statistics called adaptive Markov chain Monte Carlo. And the idea behind adaptive simulated tempering in this case is that when you're trying to move between these temperature levels, you have something what's called adaptive weights. And these adaptive weights get tweaked in such a way that you're trying to push your sample particles to move between temperature levels. So it basically has the notion of trying to avoid staying in the same place. So you're trying to basically say, try to go into a different temperature level. As soon as you go into a different temperature level, try to go into different temperature level. So you're trying to push your sample particles through these temperature levels. And you have this standard adaptive Metropolis-Hastings rule, and you have these adaptive factors that are trying to force you to explore the space more efficiently. Okay, so here I just wanted to show you that you can design a two-chain type of algorithms where you have a slow chain. This is your standard Gibbs sampler, and you have the fast chain that uses adaptive simulated tempering that moves around different temperature levels and tries to really explore the space. Right. So here's an example of the Gibbs sampler. Again, it just gets stuck, and this is what adaptive simulated tempering does. Notice that it moves around the space, and it's from an algorithmic standpoint, it's only twice as expensive as just doing standard Gibbs. And you can get much better models. This is another example where if you using standard Gibbs, it typically gets stuck. With adaptive simulated tempering, you can move around the space much more efficiently. And in terms of in terms of trying to figure out which model actually works better, interesting thing, if you're using adaptive simulated tempering, the learning dynamics becomes much more stable than using Gibbs sampling, using stochastic approximation that uses Gibbs sampling. And so there is, I haven't gotten into very specific details about what these models are doing, but I just wanted to point you out that there's lots of techniques that you could try to explore when you're learning these models, and we're not there yet. So it might be up to you to figure out the next greatest learning algorithm for these models. So just as a recap, we've talked about various different models. We've talked about deep Boltzmann machines. We can use these models for pattern completion. We can use these models for nonlinear dimensionality reduction, trying to work with text. You can try to learn the hierarchical representation. You can put more structured hierarchical prior on these models and really put your prior knowledge into these models. You can use these models for object detection, motion capture. And really exciting thing is that a lot of these models, they either match or come close or improve upon the current state of the art. And this is very exciting in a lot of different domains. And that probably has to do with a few things. For one, we have more data. The second thing is that we have faster computers. And the third thing is that we're now able to try to learn these complicated models more efficiently, right? And so this is I believe this is just the beginning of the big thing happening in the future. So just as a summary, what I've talked today is this notion of trying to compose hierarchical Bayesian models with deep networks, in particular for applications such as transfer learning. And just I wanted to re-emphasize that if you look at the deep networks, I think of deep networks as learning part-based hierarchies. It has a number of advantages. You get distributed representations, you get unsupervised learning of generic features. You don't need to rely on handcrafted features or specific features. And there is also a notion of hierarchical Bayesian models where you can try to learn the hierarchies, the category hierarchies, or how different objects are relate to each other, and you can also learn high-level class-sensitive features. Okay, thank you.